So you'll have just noted down a second reaction there with dilute nitric acid. So again, this is a contrast to the reaction we looked at with an arene, with our benzene. So with benzene, we had a look at needing the concentrated nitric acid and the concentrated sulfuric acid, and then those generated for us the NO2 electrophile, which was then attracted by the electron density of the ring in order to react there. With your phenol, you will have just seen that we can simply react phenol at room temperature with dilute nitric acid. So much less harsh conditions there. So just aqueous nitric acid would be fine, just the stuff we use on the bench acids that we use in the lab. And that we can get a substitution like we talked about before for the directing effects of the OH in the 2 position or the 4 position. So we can think about the proportions of each of these that we get as well. So with our phenol, if we substitute in the 2 position, that's there. If we substitute in the 4 position, oh, the pen's running out already, then that is going to be, maybe it's the board, that's going to be down there. But remember, you've got up here as well, and that's effectively another 2 position. Okay, so when you're reacting this mixture, I mean, you can go on and get the full tri-substitution like that. That's more common if you increase the concentration of your nitric acid. But if you are just reacting with the dilute nitric acid, then you get that mixture of products. But what you find is you get twice as much of the 2 position substitution, because there are 2 different ways of doing that, than you do for the 4 substitution. Okay, so you would expect your ratio of products in terms of proportions to be twice, for whatever amount of the 2 position, you'll have half as much of the 4 position. Okay, so the ratio would be 2 to 1 in terms of what we produce there. So the last reaction that we need to have a look at is the reaction with acid anhydrides. Now, see if you can remember an acid anhydride. So think in your head there, what's the functional group if you've got an acid anhydride? Okay, so everyone thoughts? So an acid anhydride has this in it. Okay, so oh, hang on, that would help. Yeah, it's hidden away, so surprise there for you. You can think of them basically being 2 carboxylic acid groups dehydrated, if that helps you remember what they are. Okay, so if we put 2 carboxylic acid groups like that back to back, and then we take away the water and join them up, you can see that you've got this bit here. So they do a lot of the reactions that you'd expect to have of a carboxylic acid, but they're much more reactive. So we can get the production of an ester if we use an acid anhydride with a phenol. With a carboxylic acid and an alcohol, we'd expect to produce an ester, but we're not going to be able to do that with phenol because it's much more stable. So what we tend to do when we're trying to react an acid anhydride with a phenol is first of all react with sodium hydroxide. Okay, so we have our phenol reacts with sodium hydroxide. This is just an acid-base reaction. So we were talking about this on the other video. And so we get O minus Na plus H2O. Now, we could have done this reaction with phenol, but if we go from having the lone pair of electrons in the oxygen here to having a full negative charge here, we've got our lone pair of electrons being much, much more available with a negative charge. And so you get a stronger reaction. So you don't need to learn the mechanism for this, but we're going to have a look through it anyway, because it's helpful just in understanding the logic. So I'm just going to have our phenoxide ion there. I'm going to leave the sodium ion elsewhere. And we are going to react this with just a generic acid anhydride, so it doesn't matter what it is. Okay, the two R groups, I'll just put R1 and R2, R and R1 so we can see where they're going. Now, we can think in terms of what we know about arrow pushing. So the curly arrow, the curly arrow from the lone pair of electrons is going to seek out a positive center. So where might we put dipoles? So this carbon here with a double bonded oxygen is going to be delta positive and then delta negative there. So that would mean that the lone pair on here is going to attack that there. Now, what we can then do is break this bond and then kick off the rest of the acid anhydride like that. So we can then think about how that's going to make our product. So we've got the ring, and then this, if we look up here, so this is bonded to the oxygen here. Now this oxygen is now bonded to that carbon, which is double bonded to that oxygen, which is single bonded to our R group. And so now we can see that ester group, can't we? So we've got our ester functional group there that we've created. Now we need to work out what else we've got left. So we've sorted out the kind of bit we're trying to make in the first place. So this chunk over here, so the bonding pair of electrons here now appears on the oxygen. So that means that that's going to have a negative charge. It took back its original electron, plus it got the other electron that was shared from the carbon. So it's got one extra. So that's going to have a negative charge. And then we've just got the other bits and bobs that were drawn on there. So we can just draw those like that. Okay, so that's going to be our kind of overall mechanism stage. If we were going to write this out as a full equation, and you've got this on the PowerPoint slide to write up in a minute, we would say that we've had phenol reacting with sodium hydroxide and our acid anhydride. Draw it out again there. And what we've produced is our ester. I'm going to have room to do this. Yes, this will fit. And we've produced the carboxylate salt of our acid anhydride. So that was this bit here with a negative charge, picking up the sodium ion that was up here. Okay, so we just kind of put it to one side as we were doing our mechanism and producing water. Okay, so that's our overall reaction, but we've seen what happens in the mechanistic stage there. One just general note here. So when we were drawing our carboxylate salt out here, I've put O- and Na+. That's perfectly okay. You've got to make sure when you're drawing things out that the charges are kind of consistent. So either put the O- and Na+, or just put O-Na. What you mustn't do at all, I'm always reluctant to draw out stuff you mustn't do, so just make sure this is a big X. We do not write this. So what we would not write is O-Na, because that's a covalent bond, okay? So you can't have that, but you can just write the two next to each other like that, and probably the optimal is to show that you know it's ionic, so to put those two there. Okay, now just recapping as well, so the reason we put the sodium hydroxide in is because the phenoxide ion is a better nucleophile than the OH. So if we're looking here, we've got the lone pair on the electrons attacking a positive center. So that's nucleophilic attacks. This was behaving as a nucleophile. The lone pair of electrons on a negative ion with the negative charge on the oxygen here are much more available than the lone pair of electrons in here. So that allows the reaction to proceed.